All right. So let's work on getting back to it. What we're going to be doing here is we're going to, like we said, be hanging our way up by our nails up to the next organization of the building blocks of life. So we had talked about atoms before, and now we're going to move our way up to what we would call molecules. Okay, so let me see if I can find where we dropped off last time. I think we were talking about radioisotopes. Looks something like this. And when we were talking about radioisotopes, we were talking about individual atoms, but when we're working at molecules, we're looking at working our way up to how we can get individual atoms to stick together. So instead of a joke that I was going to say, maybe it would come across better as an image. How about that? In any case, combining matter. So when we combine these atoms, we can form molecules or compounds. Now, when we talk about molecules and compounds, what's the difference between those? Well, a molecule is where we have two or more atoms bound together or bonded together, whereas a compound, we have two or more different kinds of atoms that are bonded together. So that's key. So if we were talking about, for instance, oxygen gas, right? That would be a molecule. And when we're looking at that, that would be two oxygen atoms that are stuck together. But if we talked about carbon dioxide, that would actually be a compound instead, right? Because a compound is a mixture of more than one type of atom. So when we look at molecules and compounds, somehow we're getting these different atoms to interact. And so how we're going to do that is what we're going to talk about now. Okay, so when we're mixing things together, because essentially that's what we are, we're taking these building blocks and we're starting to get them together. When most of the matter that we interact with or that exists as mixtures. So we have two or more components, and these mixtures can be as solutions or colloids or suspensions. And you look at those terms, you're like, math solution, suspended in the air, I'm not sure. Well, this is a case where definitely terminology is going to be key. So you have to know what we mean by these terms when we're talking about chemistry. So this figure should hopefully help. So a solution is where the particles are very tiny and they don't settle out or scatter light. So for instance, mineral water, right? There are different ions that are in there. Not only are there water molecules in there, H2O, but there's different ions in there like sodium and chloride, etc. A colloid is where those particles are a little bit larger and they tend to scatter light because they're big enough that the light's bouncing off of them. But they still don't settle out. So when we look at Jell-O, right, we can see that it's a little bit more viscous, and so those larger particles in there are affecting the consistency of it. When we talk about a suspension, really large particles, like in this case, like blood, individual cells, that if you centrifuge it or if you allow it to sit for a period of time, these particles will settle out, like we see here, red blood cells and even white blood cells, things like that. So these are all mixtures, though. It has to do with the size of the particles that are inside of them. So solutions we come up to in chemistry a lot, and there's two different aspects of a solution. One is the solvent, which is the substance present in the greatest amount. That's what it's dissolved in. And then we have, if you will, the solute. So the solute is going to be in a smaller amount, and this is usually going to be what you're mixing in it. So if you're making up lemonade or something like that, or Kool-Aid or something, right? The water is the solvent, and the solute is going to be the powder that then kind of mixes through it. Now, when we're talking about lemonade or Kool-Aid or something like that, you know that you can make up different concentrations of that based on how much solute you have in how much solvent, right? If you take that whole packet and you put it in one cup, it's going to be very, very concentrated, as opposed to putting it in a kiddie pool. It's going to be very, very dilute instead. So we have to be able to quantify concentrations. It's important in the body in terms of how much salt we have, how much glucose we have, things like that. So we can look at it in terms of percent. How many parts of that particular solute are in 100 parts of the solution, like 100 parts water or something like that. When you talk about seawater, that is in parts, if you will. That's parts per thousand. how many ions that we have of salt per 1,000 of water. But in any case, you can do it as a percent. So like when you're mixing things up, 10% salt solution. Like I said, seawater works that way too, but they use it in parts per thousand, so it's a little bit odd. Marine biologists, a little bit odd. You can also express that concentration in terms of milligrams per deciliter. So a deciliter is 1/100th of a liter. So again, milligrams if you're talking about mass, and deciliter if you're talking about volume, right? So you want to know how much of the solute is in the solvent, glucose in water, etc. You can also express it in terms of molarity. So this is the number of moles of that solute per liter, that's the unit, liter of water. So 1 mole of a compound is equal to its molecular weight, when you add up all of those atomic weights, in grams. So for instance, this is how we express a glucose molecule. It has 6 carbon, 12 hydrogen, and 6 oxygen. If we add up all of the molecular weights of all those atoms, we have about 180 AMU or AMU, and so that's 180 grams of glucose added into water to make a liter is going to give you a 1 molar solution of glucose. So again, it has to do with the size of the particles in that case, or the size of the molecules, or in this case, the compound. And 1 mole of any substance always contains 6.02 times 10 to the negative, or 10 to the 23 molecules of that particular substance. So that's Avogadro's number. You've maybe heard of that. Not avocados, but Avogadro's number. So we won't get into calculating any of that. Again, this isn't a chemistry class, but concentrations are critical, especially as you get into healthcare, right? If you are giving them a solution, right? If you are looking to give them a bag of saline or something like that, and you want it to be isotonic, the same concentration as their bodily fluids, or you're dosing them, right? You need to know how much you are giving them or what their current concentrations are. Okay, but getting past that and getting back to how we get these atoms to hook up, these are the energy relationships. So these are truly kind of like interpersonal relationships, right? But these are energy relationships where we get these two individuals, at least two, to interact. So there are definitely some analogies. I'm big on analogies. You'll find out very soon. There are definitely some good analogies between people and their interpersonal relationships and these chemical bonds or energy relationships as well. So in a lot of cases, we are looking at the electrons, those subatomic particles with a negative charge, and those, as they're circulating around the nucleus of that individual atom, those are towards the outside, if you will. Those are going to be what are going to interact with other atoms. So like we said, the electrons that are around the nucleus occupy these things that are called electron shells. And so the shells, I mean, you can kind of think of it as a seashell or whatever, right? It has kind of a form, an outer form. But when we look at it, the shells are also referred to as energy levels. And so when we look at these electron shells where these electrons are going to be located, there are different energy levels, kind of like different orbits around the nucleus. And so, for instance, there can be 3 shells that are circling the nucleus, and each shell can only hold a certain number of electrons. So shell 1 only can hold 2, the next one can hold 8, 3 can hold 18, etc. And the outermost, it depends on how many electrons each atom has, right? If you're talking about helium, or if you're talking about carbon or something like that, the number of protons it has is going to determine the number of electrons it has. So if it only has 1, it's going to be in that first shell. 2, it's going to be in that first shell. If we have more than 2, now 3, now we get to the second shell, etc. But the outermost shell that we're talking about here is called the valence shell, and that's the one that can potentially interact with other atoms, so to produce these chemical reactions. And again, if we look at these atoms as kind of like people, these atoms like to feel complete, and so they would like to have a complete valence shell, a complete outer shell that is totally full, right? They feel fulfilled. And if they don't have that, then they're looking at some way to fill that, right? Get close to another individual and have you complete me. So if we look at, for instance, some atoms, like we see here, helium has 2 electrons And 2 is how many it can fill in that first shell. And so it has a complete or full valence shell. Same thing in terms of neon. So here's our second shell, and neon has 8 electrons in the second shell, so it's full, complete. So these types of elements are called inert. They're not very reactive. They don't need someone else to feel complete. But there's a lot of other types of elements that are very reactive. So for instance, helium, hey, it would like to have 2 to complete this first shell. Carbon, when we look at this second shell, it only has 4, so it's looking to gain another 4 in order to feel complete. Oxygen, we look at that second shell, it has 6 electrons in its outer shell, and it would actually like to have 8 in that outer shell. So it's looking for an additional 2. So these are the types of elements that are looking to hook up. Okay, so when these atoms form bonds with other atoms, these bonds form 3 different categories: ionic bonds, covalent bonds, and hydrogen bonds. The ionic bonds are where we have an imbalance, right? If you have an individual that's a little imbalanced, then they can become very reactive, right? So the different types of, when we have an element that is in ionic form, the protons are not equaling the number of electrons, right? So it's going to have some sort of net charge. It's either going to be positive, or 2 negative. It's not going to be neutral because we don't have this balance. And so when we have an ionic bond, what we're doing there is we're transferring a valence shell, an outer shell electron, from one atom to another. And then what we find is that is going to, as we transfer those ions, we have that imbalance, and if we are more an atom that's more negative, then basically that's called an anion. And if we have an atom that has become more positive, that's called a cation. And so you can kind of think of that T in cation as a plus. So it has a plus charge. It could be a +1, a +2, or something like that, but it's more positive rather than being neutral. And so what happens here is, remember, this is all based on electrons, and electrons are negatively charged. So when you lose an electron, it's like losing something negative out of your life, right? So if you have all these negative things happening, you're going to become more and more negative. And if those negative things go away, then you become more and more positive, right? And so same thing in terms of a cation. It has a positive charge because it's lost a negatively charged electron, 1 or more, as opposed to an anion, which is gaining all these negative things and becoming more and more negative. And so just like in relationships, for these molecules and these bonds, opposites attract. So something that has a positive charge, a cation, is going to be attracted to an anion with a negative charge. So that's what we see here. So here we see a molecule, sodium chloride, that is basically formed between sodium and chloride because sodium has this extra electron here. If it gets rid of this extra electron in its third shell, then it's happier, right? Because it's got shells 1 and 2 that are complete, and now we get rid of this one and it feels balanced. Whereas chloride, it has shell 1 and 2 totally full. Shell 3 has 7 electrons in it. It's looking for another one to feel complete, and sodium is happy to effectively kind of donate that, right? So that's what we see here, is that this is an electron donation, if you will, from sodium to chloride. And what we have here then is this creates this ionic bond where we have a positively charged sodium ion that is associated with a negatively charged chloride ion. And so they combine to make sodium chloride, which is table salt. Now, when you have large numbers of sodium and chloride together, it actually forms crystals. And so if you were to look very closely at those salt crystals, right, they form little cubes, and that is because of the associations between the sodium and the chloride. And if you take that sodium chloride as a solute and you put it in a solvent like water and you mix it around, those ionic bonds are broken. Those positive and negatively charged sodium and chloride get attracted to the water instead, like going to a party and like, oh, there's lots of people I could be attracted to, and it breaks them up. And so they dissociate from one another, and that's why the salt actually disappears or dissolves. We'll see that again later. Okay, so that was ionic bonds, one of three types. Second type, covalent bonds. Covalent bonds is where we are sharing outer shell electrons between two atoms. So if we share, for instance, 2 electrons, that forms a single bond. 4 electrons is a double bond. If we share 6 electrons, it's a triple bond. So when we look at it, what we find is covalent bonds are where we are sharing them. So it's kind of like if you talk about, sharing them like, okay, we are both in need of one, but if we share them like timeshare, right? You get it on the weekends and I get it during the work week. We're both happy because I have completeness at this time and you have completeness at that time. So covalent bonds, they're sharing. So for instance, at a particular time, the 2 electrons are with that atom, and then it comes over here, and now those 2 electrons are over this atom, and this one feels complete. So it goes back and forth between the two. So if you share 2 electrons, that's a single bond. If you share 4 electrons, then that's going to be a double bond, etc. And that sharing, it's not always even. Like we said, if you're sharing like a timeshare and you get the weekends or the weekdays, that's not exactly even in terms of the number of days, right? 5 versus 2. So there are what are called polar covalent bonds where it's unequal sharing of the electrons, as in the case of water. So because it's uneven, what happens here is that the electrons tend to accumulate a little bit more on this side of the molecule as opposed to this side. So it makes this side of the water molecule slightly more negative compared to this side over here. Now there are other types of covalent bonds that are nonpolar, evenly shared between. And you can see these are single bonds right there. These are what I was talking about in terms of double bonds. This is carbon dioxide. And so carbon, like we said, is wishing it had an additional 4 electrons. And so it shares 2 that we see here, 4 over this way and 4 over that way. And so when we're looking at it, it's actually forming double bonds with an oxygen there and double bonds with an oxygen there. So that's carbon dioxide, 1 carbon, 2 oxygen. But it forms double bonds because it's doing sharing with 2 different oxygen atoms. Okay, so we had ionic bonds, then we had covalent bonds. Now, in terms of strength of these different types of bonds, covalent bonds, number 1, strongest. Then we have ionic bonds. Now we have hydrogen bonds. Hydrogen bonds are the weakest, and really they're more of kind of a generalized attraction, right? So it's like individuals that are not fully committed to one another, they're just kind of attracted. And so oftentimes, so this is going to be between hydrogen and other parts of other molecules like we see here. This is a water molecule, right? H2O. This is a variety of water molecules near each other. And we said that this is a polar molecule. So it has a slight negative charge to one side of it. And the hydrogens on another molecule are attracted to that negative side of this molecule. So it doesn't actually form new molecules with hydrogen bonds, it just organizes the molecules that are in a particular solution or the molecules that are making up a particular large molecule, the atoms that are making up a large molecule, etc., or the parts of that molecule, and it changes its form. So for instance, DNA has that double helix form that you hear about, that twisting ladder. That shape is determined by hydrogen bonds that are kind of causing that molecule to turn in a particular way, or in this case, causing these water molecules to orient relative to one another in a particular way. So again, these are the weakest bonds, and they don't really form new molecules, but they cause molecules or parts of a molecule to change their shape based on this hydrogen attraction. And you can see another example about why hydrogen bonds might be important in the case of surface tension. This is important in terms of water striders, but it's also very important in terms of us when we're talking about fluids in the body. And when we talk about fluids, remember how there's like serous membranes and things like that? Well, some of these fluid membranes that are on the surface of very small structures, that surface tension can be very strong on a small scale. And so that surface tension is something that we have to worry about and kind of work through in terms of our physiological processes, the pulling apart of these hydrogen bonds that really want to kind of pull near each other instead. Okay, so as we get towards the end of talking about how we can stick these atoms together to form molecules and compounds, then we get to what are called chemical reactions. And this is when bonds are actually formed or broken or just rearranged, like we said. So those are what we call chemical reactions. That in chemistry is basically the study of these interactions. So when we have a chemical equation, when we're writing it out, when we're writing out the recipe, if you will, about what's going on, right? A recipe takes this and this and this, and you mix these two things together, and that produces this, right? That's like a cooking recipe. Same thing in terms of a chemical equation. What we're doing is we're writing out what's going on in terms of that reaction. And there's different parts of that equation, like in math, right? We have the reactants, which are the substances that we're adding together, like the individual components of the recipe, and then the products, what happens at the end of the reaction. So we have to be able to write out that recipe. We need to know exactly how much we need of each individual substance, right? So if we're talking about I need 2 cups of sugar and 1 cup of flour and, you know, a half teaspoon of baking soda or something like that, same thing in terms of writing out chemical equations. So we have to write out the molecular formulas for the individual molecules, and as those change, as these bonds are broken or formed, that also will change. So for instance, in some very simple chemical equations, we see, for instance, hydrogen gas forming. We take 2 hydrogen atoms, and when they form a bond, it forms hydrogen gas, right? H2O. The 2 designator there says that we have 2 of those hydrogens in this particular product. Methane is, if we take 1 carbon and through bonding, we then link 4 hydrogens to it, we're going to see that we have methane, CH4. And when you have these molecular formulas, we don't write the 1. If we write the letter, that means we have 1 of that particular thing, but we don't write the 1 down below it. We only write a number down here as a suffix if we have 2 or more of those. Okay, so in any case, for chemical reactions, when we're looking at these recipes, there's 3 main types of chemical reactions. Synthesis, where we're creating things; decomposition, where we're breaking them down; and exchanges, where, as the name indicates, we're kind of switching things. So this is building, and as you can imagine with building things, that's going to take energy. So synthesis reactions, you're going to have smaller things, and you're going to hook them together to form something bigger, right? So again, if you were talking about Legos, that, in order to create a car or a boat, you have to take those individual units, and it takes energy to stick them together, right? And so that's a synthesis reaction. These usually require energy. Decomposition reactions, if you take that car or boat made out of Legos and you're done with it and you want to make something else, you might drop it on the ground. And if you drop it on the ground, that doesn't take much energy to make it go and then break apart into those small things, right? So these are decomposition reactions. You may have some decomposition reactions going on in your refrigerator right now, right? Things that are breaking down and turning weird, etc. But decomposition reactions, when we talk about digestive system, this is going on inside of you all the time. We're breaking down the nutrients that you take in into smaller and smaller components that can then be used by the cells to build what they want. Lastly, there are the exchange reactions. Again, where you see one aspect or some aspects of a particular molecule, in this case ATP or energy molecule, being transferred or exchanged to another molecule. So here we can see a phosphate. Triphosphate means 3 phosphates attached to it, 1, 2, 3. And that these phosphates, as part of this larger molecule, one is transferred to this glucose molecule, and you can see it attached there. So this is an exchange reaction. So bonds are both made and broken. We broke this one, and we created another one here. And these exchange reactions, these are typically called reversible reactions as well. So you can cause it to go one way, you can cause it to go back the other way, and those are very, very useful in the body. Another type of important reaction that we see in terms of an exchange reaction is called the reduction oxidation reaction, or a redox reaction. So by definition, atoms are reduced when they gain electrons, and they're oxidized when they lose electrons. So when you look at it, this is our sugar molecule again, C6H12O6 plus oxygen. What happens here, it gets oxidized. So we break down the sugar molecule, we get carbon dioxide, water, and ATP. And so what we find here is that this glucose itself is going to be oxidized. It's going to lose electrons, and the oxygen itself is going to be reduced. So it's going to be reduced, meaning that it's going to gain electrons. And as it gains electrons, it's going to be able to pick up the positively charged hydrogen and cause the hydrogen to stick to it in order to make this water molecule that you see here. So these redox reactions have to do with the gaining or loss of electrons as well when they're doing these exchanges. And so this reaction, as you can imagine, right, this is very, very important to us as organisms as well as individual cells, where we take in chemical energy, right, that we have one form in terms of sugar, and we can turn it into a type of chemical energy that we can store to produce kinetic energy later on, like we saw in muscles contracting, etc. Okay, now one of the things we talked about in terms of these synthesis reactions or decomposition reactions is we can write them out saying these things go to that or these things go to that, but again, it's energy which makes that happen. And so the chemical reactions are going to be what are called exergonic or endergonic. They're either going to give off energy or they're going to use up energy. And so, for instance, catabolic reactions and oxidative reactions, right? A catastrophe, it's something, things are falling apart, breaking down, right? Those decomposition reactions are often exergonic. We give off energy. Meanwhile, those synthesis reactions where we're taking small things and building up bigger things, those ones take up energy instead. And like we said, a key aspect to many of these chemical reactions in the body is that a lot of these chemical reactions are reversible. So if we took the small things, A plus B here, and we created this larger thing, what would that be called? In terms of our three types of chemical reactions: synthesis, decomposition, and exchange. So small a plus small b, and now we get AB. That's going to be a synthesis reaction, right? Two smaller things, we make a bigger thing. That requires energy. So what we would find is that's going that way. It's going to require energy. But if we go back the other way and we break down this larger molecule into its components, that's going to give off energy instead. So kind of storage and then using, storage and using. It's like going to the grocery store and stocking up on things, putting it on the shelf, and then later on opening it and using it. So we see these things as reversible, and it's very important that for some chemical reactions we can do that type of conversion back and forth. In fact, when we're talking about carbon dioxide in the body and how the cells of our body, when they're producing energy, they produced carbon dioxide. We need to transport it in the blood and exhale it and get it into the atmosphere again. So carbon dioxide is transformed into another form for transport in the blood. And when we get it back to the lungs, we got to transport it back to carbon dioxide again. So that's called a reversible reaction. And while they're not necessarily the most common thing in the body, they are very important in the body. Okay, so energy is very important for these chemical reactions to occur. The rate at which they occur can be determined by temperature. Now remember, temperature is energy, it's heat, right? So the higher the temperature, the more these molecules are going to bounce around and interact. The lower the temperature, the slower they're going to be interacting. Concentration as well. If you're looking for atoms or molecules to hook up, right? If you go to a party and you're looking to meet people and there's only a few, well, you're not going to have many reactions, right? But if it's really crowded, you have a lot more chances of meeting up and hooking up with people. Particle size as well. If it's very small, then smaller particles are usually going to increase the rate because we have these small particles bouncing around and interacting, etc. One of the last things that we see in terms of chemical reactions has to do with catalysts. So we say energy can make a reaction go, right? And we need energy. And a catalyst reduces the amount of energy necessary for a chemical reaction to occur. So it's a bit like catalysts are kind of like oil in your car, right? The engine would run without oil, but if you put oil in the car, it acts as a lubricant, and those actions occur easier. And that's also what occurs in terms of chemical reactions. So catalysts, particularly enzymes, which are biological catalysts, they make a chemical reaction occur with much less energy. It's easier for it to occur. So enzymes are very, very important. We'll talk about that in terms of digestive enzymes and respiratory and cardiovascular enzymes. Enzymes are used by most all cells in the body. They're very, very important. Okay, so for now, that's going to take us through some of the basic chemistry that we need to know as we're working our way up towards the more complex levels involved in the human body.